Hello everyone, welcome to the course on architectural design of ICs. So, last classes we have seen different kind of architecture of adder circuit, multiplier circuit, and then that we have seen that how fixed point representation can be done, that we have seen. Okay. So, these are the basic operators design we have already till now we have already learned how to do that. It is not that only this much of architectures are available on the literature or available on the market. This is just to there are, that means this field is so much rich, there are so many architectures, so many people have worked on this particular to find out the best possible architecture for their particular application. Okay. So, there are several architectures available on the that means on the literatures, but I have just gave you some of the that means brief about those architectures, that how we can improve or what is the techniques or how we can proceed to get different architecture for different applications aspects. Okay. So, that we have seen till now. So, now we have learned the basic operators design till now. It is not that only this much operators are there, but still there is so many left. That means there is that sometimes we need square rooting circuit, sometimes we need divider circuit, sometimes we need logarithmic function to be done. So, so many others, or that means arithmetic operations are also required to implement the function. Okay. So, that means in the function, that means there are several other operators too which are being used. So, considering this fact, here today we will learn one interesting that means algorithm to implement different kind of arithmetic operation. Okay. So, the structure is this, or the architecture is CORDIC architecture. So, first we will see what is the meaning of CORDIC. Okay. So, what is the algorithm of CORDIC and how it basically calculates different operators, arithmetic operation, how it does, and how, that means what are the types of operation it can done. Then from that particular point we will see that different kind of architectures to develop the corresponding hardware for CORDIC. Okay. So, let us start with today's topic, which is this CORDIC architecture. Okay. So, the full name of CORDIC is basically one acronym. So, CORDIC is basically the full form of CORDIC is coordinate rotation digital computer. Okay. So, that is why here you see this from coordinate CO, from rotation this R, and from digital DI comes, and from computer this C comes. So, the full name is CORDIC. Okay. Then where are the application, or what is the application area of CORDIC? In many DSP algorithms, or to implement many DSP function, we used these CORDIC algorithms, because what I said in the beginning, that using CORDIC we can implement different kind of arithmetic operations. Okay. So, it is being used in any linear transformation like this DFT, then Z transform, then DHT, then FFT. So, all these transform they used, this is the linear transform. So, in the linear transform basically CORDIC is being used mostly. Then not only this, specific to this linear transform only, it also used in digital filters like this orthogonal digital filters and adaptive lattice filters. Okay. So, these are the, that means these are the filters which are available in multi-rate digital signal processing, which are being used in multi-rate digital signal processing or either in digital signal processing. Then matrix based digital signal processing algorithms like this QR factorization with application to Kalman filtering, then linear system solver such as this Toeplitz and covariance system solver. So, that means this for this matrix based whether that is multiplication or this factorization. So, for this purpose also we use CORDIC or we have used, that means we have noticed plenty of use of CORDIC for deriving the hardware architecture of this particular functions, which are like this QR factorization or FFT or DHT or DFT. So, that means this application area itself, it shows that CORDIC is being used for various applications in DSP algorithms mainly. Not only it is specific to DSP, for wireless communication also we used mostly CORDIC. Okay. So, then what is the advantage of CORDIC, then how, what is the, that means what is the algorithm behind that, that we will see in this later of this course. Okay. So, the thing is that why do you use CORDIC? Why or what is CORDIC, that we have already seen. Why do you use and when do we use? The thing is that this is not only specific to why do you use, when do you use. Basically all the, that means DSP algorithms, they are mainly this MAC based. MAC based means the operational most likely multiply and then accumulate. So, multiply and accumulate means, so some multiplication, like if I say that this digital filtering. So, what we do basically, that is nothing but the summation of the multiplication of the input and the coefficients. So, that means in FFT also what we do, these two dual factors, they are being in each stage, they are being multiplied with the corresponding inputs. Okay. So, that means in each of this particular DSP function, they are most likely they do this multiply first, then they add those results and then they again process for the further stage. So, that is why we need this multiply and accumulate architecture. So, instead of this as this MAC based operation, they are that means mostly used for this DSP algorithms. So, this can be replaced easily. So, in multiplier and accumulate, for multiplier and accumulate unit, what I need? That means I need one multiplier and then I need one adder, that means accumulator. Accumulator means adder along with one resistors. Okay. So, that means now if the word length for actually what is the problem of multiplier is that if I consider n bit into m bit. So, at that time the product will be m plus n minus 1, that much bit I require to hold the product results. So, that means the word length, that is basically increased. So, after that as I am using this adder circuit, adder and then resistors. So, that means automatically it is basically increasing the hardware for that. So, if I use that kind of that means unit, let us say 100 times or 1000 times. So, that means the area will be very much higher. So, that is why this MAC basically dominates the implementation cost in some DSP function. So, that means where this cost is mostly, that means is very much critical. So, at that time we can replace this MAC by using of CORDIC. And then in the DSP approach, CORDIC helps to save the hardware cost. So, that is why we use. So, when do you use? When we have that hardware cost is one of the major, that means concern or major constraint in my design. So, at that time we can replace this MAC unit by CORDIC. Okay. So, then this, what is the basic concept of this CORDIC algorithm? Okay. So, in CORDIC algorithm it says that to decompose the desired rotation angle theta into the weighted sum of a set of predefined elementary rotation angles, which are AMI. That means what? What is the meaning of this line is that, suppose basically we use to calculate, mainly we use there are different kind of that arithmetic operation you can do, but mainly CORDIC is being evolved or CORDIC is being produced to generate the data of sine and cos. Okay. So, sine and cos means it is related to, or if I give any of the angles as a input. So, I need the corresponding the results of cos theta and sin theta. mainly it is CORDIC is being used, that means developed for use of this function in the calculator. Okay. And that has been proposed by I think J. Boulder. Okay. In I forget the year, I think I am having it. So, at that time I will say that what is the exact year it is being proposed, this CORDIC algorithm. And here that this is the, that means basic concept, or this is the concept that if I need the rotation angle or the desired rotation angle, if I say, that is arbitrary, okay, that is user dependent. So, if I say that okay, I need 90 degree, or if I need 45 degree, or if I need 30 degree, 60 degree, any degree if I mention. So, at that time, based on some predefined elementary rotation angle, it tries to calculate the desired corresponding angle. Okay. So, how we will see later. And then what is the beauty of this, that this basically this, while we are calculating this sine and cos function, only this shift and add operation is required. Means what? I do not need any, that means multiplication, and that means the operation are much more simpler. It is not that much complex, because shift and add based, that means operation is the more simpler one. Okay. So, that is why we use, or the use of this shift and add operation in CORDIC makes it lesser complex, that means lesser complex than the other circuits. Okay. So, this is the basic concept of CORDIC. Okay. So, in FPGA, this is not only that based on the FPGA as well as you can go for the ASIC design, or which is the standard cell based design. Okay. But nowadays on the current FPGA, this multipliers and adders, they are pre-built. Actually, we know this FPGA we are having the pre-built function, right. So, at the introduction I think I have already discussed that. So, but nowadays this FPGA are so much advanced, they itself contains the MAC unit from the beginning, or that is predefined in the corresponding hardware. Why this it is that means predefined, or that means pre-designed in the, or from the beginning it is being introduced in the FPGA chip itself, because at that time the performance of that MAC unit will be on the higher side. Okay. But however, for various communication techniques and matrix algorithms which requires trigonometry, the square rooting function, we need to perform this CORDIC implementation. Okay. Then how we can do that, means suppose I need to do this matrix multiplication or this matrix inversion. Actually, if I go for the image processing algorithms, that means if I am developing this image processing algorithms, the hardware for image processing algorithms. So, at that time image processing means it is basically two dimensional. Okay. So, at that time I need the, that means the processing in the matrix form. Okay. So, that means I need the operation which is not only be sufficient to, or it will be costlier whenever we will try to implement those functions using only these multipliers and adders. Then the other thing also, this square rooting, for we have to develop the circuit for square rooting. Basically this division and square rooting, we have seen multiplication and then squaring. So, division and square rooting, there the algorithms are very much similar, or the operations are very much similar. Okay. So, how easily we can do that? So, using CORDIC we can do that. So, the CORDIC algorithm based on, that means which requires only the shift and add operation, it can calculate the various trigonometric function like the square root of a square plus b square, then sin theta, cos theta, tan theta, and then other function like this division, then logarithmic function implementation. So, all this can be done using this CORDIC. Okay. So, how can be done? So, here you can find some of the, that means literature on this CORDIC algorithm, okay, which are being referenced here. So, this is not only that only this much are available. If you find on Google Scholar or in IEEE or any other, that means in any scientific journal, if you just search this CORDIC, you will find various works of different hardware architecture for CORDIC. Okay. So, here you see in 1957 by the author Jack Boulder, it is being introduced this CORDIC technique. Okay. And then how we can, that means what is the that means how it works. What we are saying that we can calculate the square root function, we can calculate sin theta, cos theta, tan theta, we can calculate this division operation, we can calculate logarithmic function, but how it works basically. Okay. So, mainly if you consider this Cartesian coordinate plane rotation. Okay. So, suppose I am having this x1 and y1, one vector, and another vector is basically that is shifted by the angle theta, which is basically this x2 and y2. The corresponding position of these vectors is x2 and y2. So, then x2 can be written as x1 cos theta minus y1 sin theta, and y2 can be written as x1 sin theta plus y1 cos theta. So, this is basically, this is just from the this is just the vector algebra. From the vector algebra we can calculate the corresponding, or we can get to know about the corresponding values of this y2 and x2, which are nothing but dependent on that. So, suppose this is the initial vector which is being rotated by the angle theta. So, this is the now the, that means after the rotation, this is the new set of values I will get. So, what will be the that value? So, that value will now that means represented, or I can get the values as x1 cos theta minus y1 sin theta, and y2 can be written as x1 sin theta plus y1 cos theta. Okay. So, based on this fact, now in the matrix form, how can I write x2 y2? That can be written as this cos theta minus sin theta, cos theta minus sin theta, here sin theta cos theta. Okay. So, why? Because this will be x2 will be what? x1 cos theta minus y1 sin theta. So, x1 cos theta minus y1 sin theta. So, and then y2 will be x1 sin theta plus y1 cos theta, x1 sin theta plus y1 cos theta. So, this is written. Okay. So, if I just that means rotate, or this rotation is basically 90 degree. So, at that time what will be its value? It will be 0 minus 1. So, at that time theta, if theta is 90 degree, so at that time cos theta value is 0, sin theta value is 1. So, 0 minus 1, 1 and 0. So, x2 and y2 will be minus of y1 and x1. So, here you see, if this is the initial vectors which is x1 and y1. So, this is the after 90 degree shift, the position will come over here. So, in this case, okay. So, here the corresponding, so this one is minus y1 and this one is x1. Okay. So, that is why the corresponding values for this x2 and y2, that will be dependent on this x1 and y1. That means, in this particular direction it will be shifted by y1, this x2 direction, that means in the x direction it will be shifted by y minus y1, and in y2 it will be shifted by x1. Okay. So, then in CORDIC what we do actually, this is the corresponding function after rotation, here what is that? Theta is my, that means the desired angle of rotation. So, that means I do not know the exact value of theta. So, we have to calculate the sin theta and cos theta for any desired values of, or any, that means user defined values of theta. So, how, that means then x 2 and y 2, that can be the, or the equation for representing the x 2 and y 2, that is x 1 cos theta minus y 1 sin theta and x 1 sin theta plus y 1 cos theta. Now, if you take common of this cos theta, it can be written as x 1 minus y 1 tan theta. So, here it will be y 1 plus x 1 tan theta. Okay. So, now we have to calculate this corresponding function of x 2 and y 2, how we can calculate. So, here actually we do pseudo rotation. What is pseudo rotation? So, pseudo rotation means here you see what is there, that means this is basically, this particular vector is basically rotated by the angle of 90 degree, okay. And this is, you see, this is basically circular, okay. But if I do not take this circular one, if I take the pseudo rotation which is just straight of this particular vectors from this particular point, that means the angle which is basically covering over here, which that is 90 degree, that means just orthogonal to this particular. So, where it is basically meeting with this, the original value was what? X 2 and y 2. X 2 and y 2 means, so this is the values of x 2 and y 2 depending on this particular function. Okay. But here instead of doing that, what we are doing? We are doing another rotation which is the pseudo rotation, and the corresponding values for that is x 2 cap and y 2 cap. So, x 2 cap and y 2 cap, how it can be, that means the pseudo rotation can be written, that is if I just cross this cos theta. So, x 1 minus y tan theta plus y 1 plus x 1 tan theta, that will be the corresponding pseudo rotation values of this x 2 cap and y 2 cap. Okay. So, now here you see the angle of rotation is correct, but the x and y values are scaled by this particular factors. Means what? Now, here actually there is a multiplication of this with this function is basically multiplied with this cos theta. So, we are removing this cos theta, means it is basically scaled by the 1 by of this cos theta. So, which is nothing but this cos inverse theta. So, cos inverse theta we can also write that as a cosec theta, then cosec theta can be written as this 1 square root of 1 minus tan square theta. Okay. So, that we will see now. Okay. So, then what will be the value of this? What will be the magnitude value of this particular r? So, initial the value, if this particular the magnitude of this, if this is r. So, here what we are doing? We are basically scaling that by cos inverse theta. So, that means now r dash will be, because of the pseudo rotation, this r cap will be r by cos theta. So, r is nothing but your square root of x 1 square plus y 1 square divided by cos theta. Okay. So, what is the, that means corresponding values of this, that is x 1 square plus y 1 square, and this r value is, r cap value is now that because of this pseudo rotation, the corresponding value is now square root of x 1 square plus y 1 square divided by cos theta. So, here actually it is being this is because of this increase, the vector r has been increased by the factor of 1 by cos theta. Okay. So, this is just the, that means the that another example of the pseudo rotation is step in CORDIC, which is what is that? That is here x 2 and y 2, x 2 and y 2, that is being that means written as this, that is x 1 cos theta plus y 1 sin theta. And if I take common, then what I said, that is that cos theta can be represented as what? That cos theta means what? Cosec theta, sorry, cos inverse theta means cosec theta. So, cosec theta can be again written square root of 1 plus tan square theta. Okay. So, 1 plus tan square theta, square root of that is being written over here. Okay. No, sorry, this is the, that means the 1 by cos theta. So, 1 by cos theta means cos theta is now basically written as 1 plus tan square theta, square root of. Okay. So, in the same manner we can write this y 1 2, in the case of y 1 this is basically here minus, this is plus. So, this is the initial vector and this is the pseudo rotating vector. Okay. So, this is the corresponding that trigonometric function, if I, that means cos theta, that is equals to 1 by inverse of 1 plus, sorry, square root of 1 plus tan square theta. Okay. So, actually what is, why I need this pseudo rotation, or what is the meaning of this, or why is this intentionally we are doing, or we are introducing this pseudo rotation? Okay. Yes, we are basically intentionally we are introducing this pseudo rotation. Why? What for the we are using? Because, and about this z I am coming, or I am discussing later. So, we have seen till now x and y, but where from this z, that is that I am coming later. Okay. So, here you see, because of this this tan of this tan theta, what we can write. Okay. So, what we can write, that can be actually first let me tell you, this z is the, that means the corresponding, actually this equation I have to write after the rotating the vectors by an angle of alpha, here it is mentioned as alpha. Okay. So, we have to, whenever we are just rotating, and what I said in the beginning, CORDIC is basically based on some predefined angles, it basically decompose those the desired rotation of angle. So, how it will decompose? So, that means in each of the step, how much is the angle I am basically calculate, that means traversing, that I have to somewhere I have to store that particular information. So, that particular information is stored in this equation, which is z equals to initial vectors, which is z I minus alpha I. Okay. So, this is the, that means this particular z term is basically used to calculate, or it is being used for mentioning the corresponding how much rotation I am doing of this desired rotation angle. Okay. So, based on this, if I use some of the predefined set of angles, which is basically where this predefined angles is basically dependent on some in the power of 2. In the power of 2 means this tan alpha I, this is basically now replaced in terms of this tan inverse of 2 to the power I. So, that means the angle is basically rotated on the based on this particular equation, which is E I equals to tan inverse of 2 to the power minus I. Okay. So, for what reason I am using this and what is the meaning of doing this? So, that we will see or that we will cover in the next lecture. Okay. So, whatever we are doing for this CORDIC implementation or whatever we are changing in these equations, they are basically intentional and there is a particular reason for that, and because of this pseudo rotation and considering this fact, this CORDIC algorithm that becomes much more, that means it becomes less complex than the other things, or this the hardware architecture that becomes very much simpler or less complex. Okay. So, thank you for today's class.